Okay, last Tuesday we studied how this Rankine cycle runs. So we determined the energy balance equation for the 4 components of this Rankine cycle. They are turbine, condenser, pump, and boiler, such as this one. So this is how we evaluate the performance of each component of an actual Rankine cycle. So today we are going to study how we can simplify this one so we can design a Rankine cycle. That is called ideal Rankine cycle. In this ideal Rankine cycle, to simplify the actual Rankine cycle, we are going to make 2 assumptions. The first one is, so there are 4 devices. So there are 4 devices. They are boiler and turbine and condenser and pump. There are 4 states. Number 1 is the exit of the boiler and the inlet of the pump. Number 2 is the exit of the turbine and the inlet of the condenser. Number 3 is the exit of the condenser and the inlet of the pump. Number 4 is the exit of the pump and the inlet of the boiler. And we produce power, turbine power, and we reject waste heat, Q that out in the condenser. We consume pump power, W dot P by the pump, and in the boiler, there is a heat addition, Q dot in. So this is a typical Rankine cycle, and our assumption is going to be we are going to assume this boiler process is constant pressure. And this condenser also runs at constant pressure. So that we can study the boiler and condenser by a simple energy balance equation. And in this turbine, we say this is isentropic turbine, so entropy S remains constant. S1, the specific entropy at the inlet should be the same as specific entropy at the exit. And we also assume the pump is an isentropic pump. That means the entropy at the inlet S3 is the same as S4. So we have 2 assumptions: isentropic pump, isentropic turbine, and the other assumption is constant pressure boiler and constant pressure condenser. So since they are, since this one is constant pressure, the inlet pressure number 4 and the exit pressure number 1, they are the same. So P4 is the same as P1. And this condenser is also a constant pressure condenser. So the inlet pressure P2 is the same as the exit pressure P3. So isentropic pump, isentropic turbine, constant pressure condenser, constant pressure boiler. So based on that, that we can plot this on a TS diagram. Temperature and entropy. And how many pressure values do we need? We have a boiler pressure that represents number 1 and number 4. And we have a condenser pressure that represents number 2 and number 3. So we only have 2 pressure values. One is high in the boiler, one is low in the condenser. So we have 2 pressure values. I'm going to make TS diagram, one for high pressure. So this is pressure in the boiler. And the other pressure is here low pressure, T of the condenser pressure. Now, number 2 and number 3 should be somewhere on this line because their pressures are this one. Number 1 and number 4, they should be on this line because their pressure value is this one, right? Then let's study the entire Rankine cycle on this TS diagram. Our assumption is, let's start with number 1. After this boiling process, what happens? Water becomes steam. And once it becomes steam, it exits the boiler. So the phase change process of number 1 is going to be right after its evaporation, which is saturated vapor. So on this TS diagram, we have compressed liquid, saturated mixture, saturated vapor, superheated vapor. Since the steam exits the boiler right after it changed the phase, it's going to be saturated vapor. That is number 1, state number 1. Then let's see what's going to happen from number 1 and number 2. We have an isentropic turbine. Isentropic turbine means entropy S remains constant. So where is entropy? The horizontal axis is entropy. So this entropy S should remain constant. S1 is S2. And what happens in the turbine? It expands. So its pressure goes down from 1 to 2. And its temperature goes down. So following this line, because entropy does not change, following this line, and the pressure becomes the condenser pressure. So this point, number 2, state number 2. Then what's going to happen in the condenser? We are removing heat. So this condenser rejects heat to the outside. So what's going to happen? At what condition? When pressure T remains constant. So it should be either this way to the right or this way. Since it is removed, it should go to the left, right? Until it becomes liquid, fully liquid, which is right here. Saturated liquid is state number 3. Then this saturated liquid enters this pressure and pump. And what's going to happen? In the pump, pressure goes up from the condenser pressure to the boiler pressure. From this condenser pressure to the boiler pressure. On what condition? When entropy S remains constant. So where is entropy? When entropy S remains constant. So S3 should be the same as S4, and pressure goes up, not this way, until the pressure becomes boiler pressure. So here. So pressure goes up when entropy S remains constant. So that is number 4. Then in the boiler, receiving heat at constant pressure. So it is at constant pressure, should be on this green. So receiving heat, not losing heat. So to the right, it becomes saturated liquid, saturated mixture, and finally becomes saturated vapor and exits the boiler to enter the turbine. So this is ideal Rankine cycle. then in this ideal Rankine cycle, how do we determine the net power? The net power, W dot net, is going to be Q dot in minus Q dot out. You remember this equation from chapter 5 for heat engine, right? So what represents Q dot in? Between 4 and 1. So Q dot in represents between 4 and 1. So this green is Q dot in. Then what about Q dot out? Q dot out is the heat rejection between 2 and 3. So between 2 and 3, what is Q dot out? This red. So what is green minus red? So this one is green. This one is red. So what is green minus red? This blue. Is this one, blue. So the net power you can produce by this Rankine cycle is the enclosed area on the TS diagram. Then once you study up to here, what do you want to do? So I was successfully analyzed this Rankine cycle. Then what do you want to do? That's it? No. We want to improve this Rankine cycle. How can you improve the Rankine cycle? By decreasing the net power? That sounds very stupid, right? We want to increase the net power. So what represents the net power? The blue. So we are going to learn how we can increase the enclosed area. That's how we can improve the performance of this Rankine cycle. So the simplest way we can do is there are, can you control this entropy? Can you increase or decrease? Sounds pretty difficult, right? So controlling entropy may be slightly difficult. What about another property? Pressure. Can you increase or decrease? Sounds simpler than, the changing entropy. So let's think about that. How many pressure values do we have? 1 and 2. So let's look at each one by one. I'm going to look at this condenser pressure. What happens if we increase the condenser pressure? This green line, this green line, this is the condenser pressure. If you increase it, it moves upward. Does it increase the enclosed area? No. So we want to decrease it. So if you decrease the pressure in the condenser, you can increase the enclosed area. So that's how we can improve the performance of a Rankine cycle. So if you, look for, any power plant nearby, the condenser pressure should be very low so that we can increase the enclosed area. So the first option to improve is going to be decreasing condenser pressure. So the condenser pressure can be decreased. If you decrease the condenser pressure, what's going to happen? This green moves downward. This way, this way, this way. This moves downward. So like that. So the turbine expands, steam expands in the turbine further down to here. So that is new number 2. and reject heat in the condenser up to here, new number 3, and the pump pressurize the system, pressurize the steam back to the boiler pressure. This is new number 4. So how much additional power you can produce by this black? This is the additional power you can produce. So decreasing condenser pressure, that's good. That increases net power by how much? This one here. Okay? That sounds reasonable. So whenever you want to design a power plant, you want to minimize the condenser pressure. That's how you can maximize the output. And that is not the only pressure we can change. We can increase the boiler pressure. Yeah, why not? Let's increase the boiler pressure. Let's see what's going to happen. This pressure goes up. So if you increase it, what is the new number 1? I'm going to use this blue. New number 1 is going to be here. Number 1 prime. Okay, so we can add this much. That's good. So in the turbine, it expands isentropically down to here. And then this is new number 2 prime goes to number 3, number 4. This is new number 4 prime. So you can add, let's use green. This much additional power you can add, which is good, but you're losing this much power by increasing pressure of the boiler. So decreasing condenser pressure always increase the power, net power. However, increasing boiler pressure does not necessarily improve the performance. It's questionable. Okay? So that's the two different, the theories, changing pressure. Okay? Then is there anything else we can do? Yes, the number 3. We don't have space, so we can use this one. So if you look at this boiler pressure, let's forget about this green. I don't like that. So if you look at this boiler pressure, isn't there something bothers you? So the steam exiting this boiler is going to be saturated vapor. Why it should be saturated vapor? Can it be superheat vapor? Should be. You can pressurize the steam, trying to increase the temperature, making superheat vapor. So you can, but the name of the device that produces superheat vapor is not boiler. It is more complicated system. So you are going to switching this boiler to steam generator. Then phase change process number 4 becomes phase change process number 5. So this one moves up here. New number 1, double prime, goes down by this much. This is new number 2, double prime. So you can add this much additional power. So having steam generator improves the performance of the system, then why don't we do that? Of course, this one is more complicated than this one. Is that it? One more way to do, which is called reheat process, reheat cycle. It's like a turbocharger in a gasoline engine. So what we do is, oh, we don't have space. So next page. By the way, feel free to let me know if you have any question. So let's assume that we already decreased the pressure, condenser pressure, did not change the boiler pressure, but we replaced boiler with steam generator. So we have a superheat vapor. Then we have a steam generator, and this is a reheat cycle. And we have a turbine, and we have a condenser, and we have a pump. So let's talk about this. So we have a high pressure, high temperature steam, superheat vapor that has been generated by the steam generator. On this TS diagram, we have the steam generator pressure, which should be very high, and we have condenser pressure very low. So this is the condenser pressure, P of condenser, and P of steam generator, So we have what? Superheat vapor, not saturated vapor, superheat vapor. So that's the starting point. So number one, enters the turbine, expands isentropically. But when you move down, you're going to end up here. Then is there any way to move to the right-hand side? Yes. In the middle of the the expansion, you stop it and then return that back to the steam generator so that it can receive additional heat. Then bring it back to the second stage turbine. But this steam generator runs at constant pressure, and this number 2 is already at reduced pressure. So there's another pressure. Oops. Which is called P of reheat process, during the reheat process. And once it returns back to the steam generator, it's going to receive heat. By how much? Q dot in between 2 and 3. And because of that, by the way, this steam generator runs at constant pressure, should be on this green, receiving heat. So it moves upward, following this green, and becomes new number 3. By the way, between from 1 and 2, we are producing power. So this one produces W dot T. And once it returns back to the second stage turbine, so this is first stage, and this is second stage, and it expands isentropically. Then it becomes number 4. Number 4, producing power isentropically. So there is W dot T. Wait, we have a W dot T here, W dot T here. We have the same thing twice. We don't want that to happen. So the first stage turbine runs at extremely high pressure. So high pressure stage. And the other one is low pressure stage. So the first one is the turbine power produced during high pressure stage. And the second one is turbine power produced during low pressure stage. And then once you enter the condenser, now we are rejecting heat, Q dot out, until all the vapor become liquid. Number 5, saturated liquid. And then it enters the pressure, a pump, isentropically, temperature goes up, pressure goes up to number 6. And receiving heat between 6 and 1, Q in between 6 to 1 goes in. So its temperature goes up when pressure P remains constant. In other words, on this green line. So this is the typical power you can produce by the standard Rankine cycle. But with this reheating process, you can add this much power. Okay? So we have 2 different designs, standard Rankine cycle, reheat cycle. But are you happy with this one? Maybe there will be, the another unique way to improve the performance. Yes, there is. This is called saturation curve. So on top of this, the point that is called critical point. Above this critical point, water doesn't exist as typical water. It's going to be super critical water that has the characteristics of both vapor and liquid together. Of course, it's going to be under extremely high pressure. But if you can increase the pressure of this steam generator beyond this critical point, could be very complicated, but we can. Then we can move this one beyond this critical point. So we can add, this is the last one, this much additional power. That is called supercritical Rankine cycle with the reheat. Okay. So how many modifications? 1, 2, 3, 4, and 5 supercritical. Reheat process. That's going to add this blue. Okay. So there are 5 modifications that you can make. Any question? That's everything about Rankine cycle. So the standard Rankine cycle, decreasing pressure, decreasing condenser pressure, increasing boiler pressure, introducing steam generator, introducing reheat process, and supercritical steam. So those are 5 modifications. So now, what do you want to do? I want to evaluate the performance of this Rankine cycle, these Rankine cycles. Then how can we do that? We can use thermal efficiency. How can we determine thermal efficiency? That's what we are going to study. Let's go with the simplest one. We have only 4 states with boiler. Then, if you want to determine, let's say, thermal efficiency. Excuse me. How can we do that? Net power we develop divided by the rate of heat transfer we provide. So desired output over required input is the way we determine the efficiency. And what is the net power? How many powers do we have? Turbine power and pump power. So turbine power is the one that we produces. The pump power is the one that we consumes. So the net power is going to be turbine power minus pump power divided by Q dot in the boiler. Now the question is, how do we determine the turbine power, the pump power, and the Q dot in? We can do that by using specific enthalpy H1, H2, H3, H4. So we have 4 H values. Turbine power can be determined by mass flow rate times the difference in entropy, as we learned from this analysis. You remember that, right? Or this one. Turbine power, W dot T is H1 minus H2 times M dot. How do we determine that? Simple. So there is a turbine power, inlet is H1, exit is H2. Between H1 and H2, which one is greater than the other? So out of H1, we produces pump turbine power, so the leftover is H2. So H1 is greater than H2. So turbine power is going to be M dot times H1 minus H2. If it is H2 minus H1, it becomes a negative value, which is incorrect, right? What about pumping power? M dot times between H3, H4. Pump power is added, therefore H4 should be greater than H3. So H4 minus H3 to make this to be positive. Divide by Q dot in. M dot times what? Between H4, H1. Q dot 1 and Q dot in is added to H4 to make H1. So H1 should be greater than H4. So this one is H1 minus H4. Then you can cancel M dot. So that's how you determine the thermal efficiency of this standard Rankine cycle. Which wasn't that hard. But when we have this reheat cycle, how many H values are we going to have? 1, H1, 2, H2, 3, H3, H4, H5, H6. So we have 6 different specific enthalpy values. If you know them, we can determine their efficiencies. How? Efficiency of this reheat cycle can be determined by the same rule. The net power produced by the rate of heat transfer goes in. So how do you determine the net power? How many powers do we have? I forgot to add pump power. So we have 3 powers: pump power, the turbine power during the high pressure stage, the turbine power produced during the low pressure stage. So the net power is going to be this one plus this one minus this one. W dot T HP plus W dot T LP minus W dot P over how many heat transfer into the Rankine cycle? 1 and 2. Q dot in 6 to 1, Q dot in 2 to 3. So Q dot in 6 to 1 plus Q dot in 2 to 3. So how do we determine high pressure turbine work power? The same rule, m dot times what? Between 1 and 2, 1 is the inlet, 2 is the exit. 1 is greater than 2 because we produce this one. So H1 is greater than H2. What about low pressure turbine power plus m dot? The inlet of the low pressure turbine is 3, the exit is 4. Between 3 and 4, we produces WT, so 3 should be greater than 4. So it's going to be H3 minus H4. H3 minus H4 minus the pump power, m dot. The inlet of the pump is 5, the exit of the pump is 6. The pump power is added, so H6 should be greater than H5. So m dot times H6 minus H5 divided by Q dot in 6 to 1, m dot between 6 and 1. Between 6 and 1, Q in is added. So H1 should be greater than H6. So it is H1 minus H6 plus Q dot in between 2 and 3. Between 2 and 3, Q in is added to 2. So 3 should be greater than 2. H3 minus H2. You can remove m dot. That's how you determine the thermal efficiency of the reheat cycle. That's everything. The end. So that is everything about mathematics. Let's talk about, so what's going to happen in reality. So these are how we design the ideal Rankine cycle. However, the actual Rankine cycle may not have this much thermal efficiency. Because of what? Here we assume that everything is ideal. Constant pressure boiler, constant pressure condenser, which are ideal. Isentropic turbine, isentropic compressor, which only happens when there is no irreversibilities, which is only ideal. You can only design if you are the god of engineer, right? So in reality, the thermal efficiency is going to be less than that. But what is the main problem in the power plant? The main problem is going to be the way we produce heat. So if it is a nuclear power plant, the main irreversibility is how we, induce nuclear reaction. If it is concentrating solar power, then the main irreversibility is how we concentrate the sunlight. If it is fossil fuel power plant, is the main irreversibility is how we, burn this fossil fuel. So that's the main issue. But that's not our, the interest of the study. We are interested in this Rankine cycle, how we actually produce mechanical power. Then, in this Rankine cycle, what is the main issue? Boiler, turbine, condenser, pump. The main irreversibility comes from the turbine. So, in reality, the ideal Rankine cycle has vertical line for the isentropic turbine, constant pressure condenser, isentropic pump, constant pressure boiler, but in reality, entropy should increase. While it is going from 1 to 2, entropy should increase. Entropy is here, so we need to move to the right. So in reality, this one goes this way. So this much increase of entropy. What about, the pump? Entropy should increase, not vertically up. It lean to the right because entropy goes up. So this way. So the actual, the enclosed area is going to look like that. Then you may have a question. I think the blue looks bigger than red. So something is wrong here, right? So our understanding is that when we have an ideal Rankine cycle, we should have the largest enclosed area. But due to the, the irreversibilities, there is an entropy increase. There's entropy increase. So there's a slight decrease in the area, but there's a much larger increase in the turbine. So the actual, the enclosed area, blue, should be larger than red. Am I right or wrong? It's very simple because you have a 50% chance to be right. It's going to be right or wrong, right? There is nothing in the middle. According to this TS diagram, right. However, in reality, from what we learned, we know that is wrong. So what is wrong here? In the TS diagram is wrong. So we only considered the turbine is not isentropic turbine. Pump is not isentropic pump. But there's one more assumption that we made. The boiler is constant pressure. The condenser is constant pressure. So what actually happens is, yes, it is right. There is an increase in, the entropy. So we are adding this much area. There is an increase in entropy. So we are losing this much area. But the boiler is not constant pressure. Condenser is not constant pressure. Oh, I have to, use this blue. So this is the actual enclosed area, much smaller than this one. Okay. So that completes chapter 8. Any question? So what is the highest thermal efficiency today's supercritical plants achieve thermal efficiencies up to 47% in the commercial sector. That's very high. How do we know? Let's compare this Rankine cycle with another, the power, the conversion model. Is there any other way to produce electricity other than Rankine cycle? Solar panel. What is the typical efficiency of solar panel commercially? Between 10 to 15% compared to that value. Dramatically low. No, I heard that, somebody, developed like a 35%, the conversion efficiency. Yes, in the laboratory. In the commercial sector, it's going to be dropped by 3 times. So, in the laboratory, the solar panel was able to achieve over, the 35 or 40%. But, in reality, there are lots of, the challenges, such as maybe dust on the surface, and the sun is moving. So unless you are holding this solar panel following the trajectory of the sun or this cloud, so you need to, you need to be as tall as the cloud. So they're holding this solar panel over the cloud, and then you can achieve 35% or 40%. But here in the commercial sector, typically between 10 to 15. That means that that we have a large the room for improvement in the sector. But in terms of the way we produce electricity, we still need to rely on Rankine cycle, unless we can live another 100 years or so. Okay. So that's everything about the theory part of this Rankine cycle. So what we are going to do? We are going to solve a few problems that are similar to your final exam. Okay? In the final exam, you will see a vapor power plant. One may have a steam generator, or one may have a reheat process. One may have a, the supercritical, the systems. So depending on the, the characteristic of the vapor power plant, you may be asked to determine the thermal efficiency or backwork ratio or something like that. Then it could be better if we practice before the final exam. So that's what we are going to do. I prepared 2 problems, the simplest one and the hardest one. So what is the simplest one? The one with the boiler. So we have a saturated vapor. So let's solve this problem together. So whenever you have a vapor power plant, that it is convenient to draw the schematic of this Rankine cycle. That means we have a boiler, we have a turbine, and condenser, and pump. It is convenient to memorize in this way. BTS. No, I'm sorry. That's a BTC, Bitcoin price. I was kidding about that. Kind of, the hot issue these days, right? So there's a heat transfer into the boiler, that is Q dot in, and there's a turbine produces power, W dot P, and condenser, we reject heat, Q dot out. This pump consumes power, W dot P. And how many states do we have? 1, 2, 3, and 5? No, 4. So the first thing you want to do when you analyze any Rankine cycle, you need to determine H value at each state. How many states? 1, 2, 3, 4. How many H values? 1, H1. 2, H2. H3. and H4. So finding these property values are the number one thing that we need to do. Before we going forward, it is convenient to use TS diagram, and since we already studied TS diagram, why don't you make one? How many pressure values? We know boiler pressure and condenser pressure. So there's a boiler pressure pretty high, and we have a condenser pressure pretty low. And what is the starting point? There is no steam generator, so we don't need to worry about superheat vapor. It's going to be saturated vapor. So where is the saturated vapor? Compressed liquid, saturated liquid, saturated mixture, and saturated vapor right here. That is our starting point, the turbine inlet condition, number one. And how this turbine runs, we just studied isentropically. S1 is the same as S2. Isentropically, entropy S remains constant. So S1 is S2. So we have this straight line, vertical line, down to number 2. That is the exit of the turbine and also the inlet of the condenser. What happens in the condenser? The condenser runs at constant pressure. P2 is P3. And if P remains the same, you should be on this green line, right? And we are losing heat, so we move to the left. And the steam can only exit the condenser when it is completely liquid. Number 3, saturated liquid. And then number 3 enters the pump. What happens in the pump? Pressure goes up from condenser pressure to the boiler pressure, from this green to this green. At what condition? Isentropically, S3 should be the same as S4. Where is S? The horizontal axis. So there's S3 should be the same as S4. So we have a vertical line going above, going upward. So there's a number 4, compressed liquid. What happens to this number 4? Number 4 enters the boiler, receiving heat at constant pressure, following this green. So this is what happens. Okay, I guess we are ready to solve this problem. How do we determine H1? Oops. Oh, property table. I have it. So it is saturated vapor at 16 megapascal. Saturated vapor at 16 megapascal. If you know this, then can you determine H? Yes. H should be saturated vapor, Hg. At what condition? 16 megapascal. Can you find Hg at 16 megapascal? Yes. 16 megapascal, 160 bar, right? 1 bar is 0.1 megapascal. (160 megapascal). And what is the one that we're looking for? Hg. So the number we are looking for is this one, 2580.6. That is the specific enthalpy of saturated vapor at 16 megapascal. 2580.6. This number. 2580.6 kilojoule per kilogram. Oops. Then what's the next? Okay, so we have a isentropic expansion in the turbine, and what is the condition at state number 2? The pressure is 8 kilopascal. Okay, we know pressure. So for this pH2, we know pressure P2 is 8 kilopascal. Do we know anything else? No. Can you determine H2? No. So you need to find another property at number 2. What is that? P2, P3, yeah, P3 is 8 kilopascal. Anything? Oh, S1, S2. So the specific enthalpy at state number 2 is the same as specific enthalpy at state number 1. Can you determine S1? Yes. S1 can be determined by the same rule as G at 16 megapascal. What is it? At 160 bar, Sg is this number. Here. 5.2455 kilojoule per kilogram Kelvin. Now, we know P2S2. So this is S2. So we know P2S2. Can you determine H2? Yes. What is the phase change process? State number 2, it is on this green, compressed liquid, saturated mixture, saturated vapor. So it's going to be mixture. If you have a saturated mixture, do you know any other equation? Any equation? Yes. S2 is SF plus quality X2 times Sg minus Sf. This is the linear interpolation equation for saturated mixture. Yeah, we know that. Then what about H? H2 is HF plus quality X2 Hg minus Hf. Then to determine H2, what we need to know, the quality X. Then what is S2? We found that, this one, 5.2455. Do we know SF? We do not, but we can find it from where? 8 kilopascal. So SF at 8 kilopascal. At 8 kilopascal, 0.08 bar, because 1 bar is 100. SF is this number, 0.5926. Sg is this number, 8.2287. SF, this number, 0.5926. Can you determine X2? Yes. What is X2? 0.6091. 0.6091. That goes to X2 here. Now, do we know HF? Yes. At 8 kilopascal, HF is this one, 173.88. What about Hg? This one, 2577. 2577. HF, again this one, 173.88. So we have everything. Can you determine H2? Yes. If you do, what is H2? 1637.6 kilojoule per kilogram. So this H2 is going to be 16 37.6 kilojoule per kilogram. Now, H3. What is the phase change process of this number 3? Saturated liquid. Can you determine saturated liquid at 8 kilopascal? Yes. It's going to be HF at 8 kilopascal. Oh, wait, I think we already found that. HF at 8 kilopascal. HF at 8 kilopascal. We have here 179.88. 3.88 kilojoule per kilogram. Now the last one, H4 of compressed liquid. We cannot assume that this one is similar to the properties of saturated liquid because the pressure is too high, 16 megapascal. So what can we do? We can use a compressed, the liquid table. However, it takes a lot of time. So let me give you one equation. The equation for compressed liquid in a Rankine cycle can be determined by, you can use that in the exam, H3 plus V3 times P4 minus P3, the exit pressure minus the inlet pressure. This one looks much simpler than using a compressed liquid table. So please use that one in the exam. Then what is H3? Oh, we already have it. 173.88. Can you find V3? What is V3? The specific volume of saturated liquid. Specific volume of saturated liquid at 8 kilopascal. What is it? This one. 1.0084 times 10 to minus 3. 1.0084 times 10 to minus 3 cubic meters per kilogram. What about P4? That is the pressure of the boiler. 16 megapascal. I don't like megapascal. 16,000 kilopascal. Do not use different units in the equation. Always convert to whatever you are familiar with. In this case, kilopascal, not megapascal. Don't do unit conversion in an equation. Do it before that. 8 kilopascal. So we have everything. Can you determine H4? Yes, 190.01 kilojoule per kilogram. So we found all the H values. Here H1, H2, H3, and H4. So we are ready to solve this problem. So what do we want to determine? Number one, the net power developed. What is the net power? We have two powers, the turbine power and the pump power. The net power is going to be turbine power minus the pump power. Okay, sounds simple. A, the net power developed can be determined by the turbine power minus the pump power. Do you remember how to determine the turbine power? Yes, m dot times the difference in H. It's going to be m dot times the difference in H. H1, H2. Which one is greater than the other? H1. H1 minus H2 minus turbine pump power m dot. It is between 3 and 4. Which H is greater than the other? Of course, H4 is greater than H3 because there is a power goes in. So it's going to be H4 minus H3. So that's how you determine the net power. What is the mass flow rate? According to the problem statement, it says 120 kilogram per second. 120 kilogram per second. H1 here, H2 here, H4 here, H3 here. So can you determine the value? Yes. 1.112 times 10 to 5 kilowatt. So once you find all the H values, any, the post-analysis, such as finding net power, finding thermal efficiency, and etc., they are very simple. So the key, for the final exam is going to be, can we determine the exact H value at each state? That's going to be the key, okay? And you need to show how you got those H values clearly to earn the full credit for that problem in the final exam. Then, what is the part B? B, the rate of heat transfer to the steam passing through the boiler. If you look at this schematic, what goes into the boiler? Q dot in. So let's find Q dot in. How do we determine Q dot in? It's going to be m dot times the difference in specific enthalpy between 4 and 1. Between 4 and 1, which one is greater than the other? H1 is greater than H4 because it is receiving heat. So m dot H1 minus H4, that is Q dot in. Do we know m dot? Yes, 120. Do we know H1 here, H4 here? Then the answer is 2.869 times 10 to 5 kilowatt. Number 3, the thermal efficiency. How do we determine the thermal efficiency? The efficiency is desired output, the net power, over required input, Q dot in. So this one divided by this one. 1.112 divided by 2.869 is going to be 0.388, approximately 38.8%. Less than the maximum value of a supercritical, the power plant system that was about 47% because there is no steam generator, there is no reheat process, etc. The last one is a little bit tricky. It says, what is the mass flow rate of the condenser cooling water? So what is the mass flow rate of the condenser cooling water if the cooling water undergoes a temperature rise by, the 18 degrees Celsius? So this Q dot out, the heat rejection from the Rankine cycle, should be observed by the cooling water, right? So this Q dot out actually goes into cooling water. Then how much energy change of the cooling water? M dot specific heat times temperature difference, T out minus T in, which is the equation that we studied in chapter 4, right? For the heat exchanger. That's the, the problem in number 2 of your second exam, right? Please calculate the rate of heat transfer within the heat exchanger from the steam to the cooling water. So what is the specific heat? 4.18 kilojoule per kilogram degree Celsius. What is the temperature rise? 18 degrees Celsius. What is Q out? This one minus this one. 1.757 times 10 to the 5th kilowatt. So we have everything. Can you determine m dot? Yes. How much? 2,335 kilogram per hour. Wow, that's a lot of water, right? Only to produce about approximately 100 megawatts of power you need to have 2,300 kilograms of water every second. How heavy is it? That's the, about, approximately the weight of F-150. That's pretty heavy, right? So you need that every second. That's why you cannot build this giant power plant in the Chippewa River. It's going to boil, right? So you need to place that where? In the Lake of Michigan. So if you drive to Chicago, you see there are lots of, the power plants, the near the coast. Why? They need this much cooling water. So that completes the first problem. Any question about that? Q out is this Q in minus W net. So this one minus this one. Then the next problem, so I told you that this is the easiest one. The next problem, we are still writing here, right? The next problem, we have a steam generator. So we have a superheat vapor at the inlet of the turbine. Supercritical reheat cycle with a isentropic turbine efficiency of 78%, isentropic pump efficiency of 82%. So this one is, I think, the hardest problem, that we can see in this chapter. So if you can solve both problems, I won't see any problem for you to, to solve the problem in the final exam. Okay. So this is like a ultimate boss, like a turtle when you play Super Mario, right? Okay. So that's it. And see you on Tuesday. We are going to solve this problem and, the part chapter 9, the last chapter, gas power system.